We are presenting novel ensemble diversification methods for open set scenarios. This work was conducted under Amazon by Miriam Farber, Roman Goldberg, George Leifman, and myself, Galnovich. Ensembles aggregate predictions given by several models trained on the same task. Diverse ensembles reduce the variance in the prediction, as the potential bias of any individual model is compensated by the others. Diversity helps to reach a reliable consensus. The open set scenario tests how well do we handle outer distribution inputs. Here we aim to utilize the ensemble diversity to uncover disagreements. With a diversified ensemble, the interpretations of each model should be so different such that a discrepancy should be easily caught. However, we have to ensure the consensus remains on in-distribution images. We first present a feature-based diversification method inspired by Deep Dream. Models are trained sequentially, and after a single model is trained, we capture the features utilized automatically by process of distillation. The distillation process matches each image from our training set with a close hallucination. Given a model and an image, we iteratively apply a gradient step onto a blank image, bringing it closer, in the view of the model, to our target. Feature-based diversification loss, or FDL, forces the new model to learn features that are dissimilar to its predecessor. We train a model on matching labels, create the model's distillations, and train the next model to our task while forcing it to avoid the representation of its predecessor. You can look at it as a form of anti-teaching, where the teacher is asking the student to avoid his ways. Here is a visual example of the CFAR embedding space. Each color represents class embeddings, and the outlined dots represent distillations. F2 shifted F1's encoded representations to an undecidable space, changing the whole embedding map. The second diversification method we present is the open set correlation reduction loss, or OSCRL. The method explicitly enforces the correlation reduction between simultaneously trained models. The ensemble is trained to succeed in the top class predictions while keeping off-target predictions decorrelated over the models. Here is the visual example of the embedding space with class centroids marked. Notice the classes shift when increasing or balancing a hyperparameter, demanding more decorrelation. Visualizing with GradCam, we can provide examples of diversification of explanations. Here, each column is an ensemble of 3 models. Notice how the explanations grow diverse with the weight of our demand. This also translates into counterfactual explanations, relevant for the rejections of out-of-distribution inputs. In our classification experiments, we train on CFAR 10 and 100 and mix in out-of-distribution images from TinyImageNet into the test set. The outlier detection is set as any non-unanimous ensemble vote. Here, OSCRL outperforms previous methods. This persists when varying the ratio of in and out-of-distribution samples. OSCRL mostly dominates across the board. We also experimented with re-identification tasks on Market 1501. Here, we aim to match test inputs with their pair in a gallery, or reject them if no match exists. FDL yields the best result in this case, outperforming the baseline by up to 30%, with OSCRL standing as the second best. Practical face recognition systems also operate in an open set scenario. We trained our ensemble on a version of MS Celeb and tested it on labeled faces in the wild. We get to see consistent results throughout. To conclude, FDL trains an ensemble sequentially to automatically enforce learning on contrastive features. OSCRL enforces diversity by decorrelating non-target classes. And we show our method's effectiveness in both classification and re-identification tasks. Thank you for listening. Be sure to read our paper, where we dive deeper, discuss, and compare our methods.